right, everybody, it's time for us to get started. So here's the information I want to start today with. First thing is, we got a homework assignment to do on Friday. So homework 5 is doing. Test 2 is on Wednesday. Say that again. A week from today, April 29th. We got a study guide for that. It's up online as well. We're going to have some study sessions for this. So study sessions on Monday and right Tuesday. And I think we said did we say from 5:30 to 7:30? Is that right?
That's what I have written down.
Okay. In this room. Okay, so that's what that. Now, yes, they will be taped, and I'll put them up. Yeah, that's right. And so I'm just going to be helping you go through the material, repeating definition, going over proofs. That's what I plan on doing. Well, there's homework to do. It's homework 5. And one of the things I want to start off with is that, look, I hope you remember, a student came by today, Audra, and I think it was Audra, and asked a question. Might have been Chuck. Wait a minute, Chuck, was it you? It was Chuck. I'm wrong. It was Chuck. Chuck came by today and asked a question about the boundedness on some neighborhood. And I don't know what examples I've done, but I want to do an example so that you can model it and say, okay, I understand. So first of all, let's recall the definition. What does it mean for a function to be bounded on some neighborhood? Wait just a second, I'll get this turned the right way. Definition. So a function, let A be a subset of R, F goes from A to R, and C be a cluster point. Of A. Then F is said to be bounded on some neighborhood of C if there exists a delta neighborhood B sub D of C. So those are all the points that are within delta units of C. Such that for all x element of the domain intersected with this delta neighborhood of C. I'm sorry, I made a mistake. There exists this delta neighborhood of C, and an M that's greater than or equal to 0, such that for all x elements of the domain intersect the delta neighborhood of C, f of x inside absolute values is less than or equal to M. All right, so let's look at a picture, and then let me make sure to do an example. So we're going to do an example, look at it graphically, and then the algebra part of it, the symbolic reasoning behind it. I don't want to do the same example I've been giving you. let's let, so as an example, let's let f of x be equal to 3x minus 2. Show f of x is bounded on some neighborhood. Let's say the number 1. Let's make it the number minus 1. Minus 1 is what it is. Okay, so here's what I'm thinking. This isn't perfect in terms of, I mean, it's very analogous to what I'm asking you to do, but it isn't perfect. Okay? So we'll do a little thing here. Okay, so first of all, graphically, what does this graph look like? Here's minus 1. If I let x be minus 1, I mean, this is a linear function. We get out minus 5. 1, 2, 3, 4, 5. Yeah, bam. If I let x be 0, we get out minus 2. If I let x be minus 2, I would get out minus 8. So 6, 7, 8. And this is the way it looks. Okay. So look, I'm talking about minus 1. I want to say this. If I put some region about minus 1, equally spread about minus 1, to the left and right, okay, will there be some number out there such that the absolute value of f of x for those numbers that I'm looking at in the region, I'm putting about minus 1, the absolute value of the output values will be less than a particular number. So here's what I'm going to do. It seems like if I just put this region right here, then look what the output values run from. They run from this output value to this output value. Is that okay? In here. Well, their absolute value will be up here, and they'll be less than some number, won't they? Is that okay? So it seems like they'll be bounded. But now let's get to the nitty gritty of the problem. I'm going to do this. Instead of putting this, I'm going to pick one unit about minus 1. I'm going to pick one unit. I'm going to let delta be minus 1. I'm going to let delta be equal to 1. I didn't have to, but that's one I picked. And you can't just let delta be anything. For this particular problem, you can. But not for all problems, okay? Not for all problems. Because if you take 1 over x, let me get right in front of the camera. You take 1 over x. 1 over x, let's see what its graph is like this over to the positive. Is that okay? So here, I'm going to draw right here. I'm going to erase it. Here's 1 over x. It doesn't look like that. Is that okay with everybody? And if you want to show that it's bounded in some neighborhood of 1, you've got to really pick some small numbers close to 1, because as you get bigger delta values, as you get closer to 0, it's unbounded about 0. Does that make sense? So you do have to watch what your delta value is. But this guy, for being linear, it really didn't matter. I'm going to let delta be 1. Okay? The domain here is all real numbers. That's all right. So note when, so what am I talking about? I'm talking about when, I'll say it this way. Note, v sub delta of 1, of minus 1, that's what we're talking about the neighborhood about. What is that equal to? That's equal to the set of all x values such that what? The absolute value of x minus or minus 1 is less than, and delta in this case is 1. That's really says this. So for all x element of v sub delta of 1 or minus 1, we are talking, for those we are talking, considering x values, elements, x values, x, such that the absolute value of x plus 1 is less than 1. Okay. So that means for all x element of b sub 1 of minus 1, rewriting that last inequality involving absolute values with something that doesn't involve absolute values, I'd have minus 1 is less than x plus 1, which is less than 1. Is that okay? So for all x element of b sub 1 minus 1, we have that minus 2 is less than x is less than 0. So I subtracted 1 from each part of this inequality. That's what I did. Look, I didn't do anything fancy. I subtracted 1 from every spot. Nothing to it. But wait a minute. Let's go back here. If you look at the delta, the 1 unit about minus 1, you look back here at the graph. What are we talking about? We're talking about being 1 unit from minus 1. Well, that means you're either minus 2 up to 0. Well, that's what we just wrote. That is exactly what we just wrote. Okay? But instead of seeing it graphically, we're seeing it now symbolically. Now, what we want to do is find some m that the absolute value of f of x is less than that m, less than or equal to that. That's what I want to do. So I want to be talking about f of x. I want to be talking about the absolute value of f of x. Well, you can tell I'm Greek. Sitting here talking like this. Well, that's the Greek person. Now listen. If I want to talk about the absolute value of f of x, I got to have f of x involved. What was f of x in this problem? It's 3x minus 2. So somehow I got to be talking about 3x minus 2. And what I'm hopeful to have up here is 3x minus 2 sandwiched in between some positive value and its negative. So I can talk about its absolute value. That's what. So I want to get 3x minus 2 because that's what f of x is. Well, I don't have 3x minus 2. I just got x. So the first thing I'm going to do is multiply everything by 3. This isn't greatly, I mean, it's very analogous to the problem I gave you, but it isn't perfect, okay? You've got to be careful, but you're going to do a similar process. Multiply everything by 3. So for all x element of b sub 1 minus 1, we've got, I multiply everything by 3, minus 6. I want to change the sign of the equality. 3x less than 0. All right, what else I got to get to f of x involved? Minus 2. That's right, Brass. That's what I'm going to do. I'm going to put for every x in this neighborhood, we have minus x minus 2. Isn't that minus 8 is less than 3x minus 2 is less than what? Minus 2. So here, I'm going to write down one more inequality. Remember what I'm looking to do, John, is I want to get a negative number bounded in f of x being bounded by the positive version of that negative number. So here's what I'm going to say. So for all x, Calvin, in this neighborhood, well, minus 8 is going to be less than 3x minus 2. And that's really less than minus 2. But I would like to put a big positive number here that corresponds to this number over here. So instead of putting minus 2, look, if you're less than minus 2, I tell you, you've got to be less than 8. Why do I want that? Because I want to be able to say something about the absolute value of f of x. And there's f of x right there. Oh, yeah. Let me get excited. Part Greek from Alabama. That means I speak Southern Greek. So, for all x in b sub 1 of minus 1, we have the absolute value of 3x minus 2 is less than, I'll say less than or equal to. What number? What's over there to the right? What number? 8. That's our m. Is that okay? So when we produced a neighborhood, 1, the neighborhood of delta 1, about minus 1, such that for all x in this neighborhood, the absolute value of f of x, the absolute value, are less than or equal to some positive number. And that's 8. Thus, f is bound on a neighborhood of minus 1. Is that okay with everybody? That's the way to do the problem. And if I hadn't done one like this before, I apologize. Because there is a little bit to it. You want to write down f of x involved in the problem, somehow, maybe, or some relationship to f of x, from the delta neighborhood information. Okay? That's what you want to do. So we did that. This is a good problem, I think. What I'm asking you to do is not exactly the same, but it's darn close. Very close. We okay with what I did? Chuck, we're good with that? Yeah, I'm glad. Megan, is that all right? How did I get there?
I know that's what you wanted, but would you just...
Okay, so wait just a second. I like Megan's question very much. There's two reasons I like it. Number one, it's important. Number two, I can answer it. So the question she said was, how did I get the 8? She said, I know you want it. Why do I want it? I want it because I want to say something about the absolute value for x minus 2. And so we know to be able to say something about the absolute value, we need a negative number here and its positive version over here. So how can I just write down A? What I'm doing is I know that 3x minus 2 for these x values is less than minus 2. If this quantity is less than minus 2, Megan, I tell you what, it's less than 0. Because it's less than minus 2. And if it's less than minus 2, it's going to be less than 3, isn't it? Because if it's less than minus 2, it's going to be less than 3. And if it's less than minus 2, then it's going to be less than 8. Because 8 is bigger than, that's right. So what I'm doing over here is I'm saying, if A is less than B, and B is less than C, then A is less than C. Is that okay? So this is less than minus 2. Minus 2 is less than less than 8. And so 3x minus 2 is less than 8. Is that okay? And the reason I wanted that is because I want to be able to say something about the absolute value. Oh, outstanding. What else we got today? Well, I want to open up the floor to any questions people might have for the homework. Besides that, anybody want to see anything done? Anybody want to see a problem? Analogous problem done? You can ask anything. Okay. Something happens later on you want to ask about? Feel free to raise your hand. It's okay. Melissa, do you have something?
I was like, can you do an example of number 6?
Sure.
Okay.
Absolutely. Somebody asked about number 6. Okay. I'm going to call it 6 star. Example, okay? So it's something like number 6. It says show minus 7x, f of x equal to minus 7x plus 5 is continuous at x equal to minus 3. That's the problem I made up. Very much like the problem that we're being asked to do. And the way I intend for you to do it is by the definition. Okay. So here's one of these epsilon delta definitions. That's what I'm looking at. Okay. Proof. We let, what's the first thing we'll write? Let, y'all got the same format? Epsilon. Let epsilon be greater than 0. Be given. What the heck we look for? What about it, Brad? What we look for? We need a delta. That's right, we're looking for a delta. Greater than 0. Such that what? Such that
for all x and r.
And it's R in this case because it's the domain of F. So here we're talking about the R with what?
Absolute value.
Oh, we don't have 0 here? No, we don't. 0 is when we're talking about a limit. So here it's just absolute value, just like what John was saying. X minus 3. X minus C is less than delta. Then the absolute value of f of x, well, what's that?
Minus
7x plus 5, that's f of x. Minus what? F of c What's that? It's f of minus 3. So it's f of c. Here, I'll write this a little slower. F of minus 3 is less than epsilon. This is what I want to force to happen. Now listen, this is the part I want to make happen. And I make it happen by choosing the right delta to force x to be close enough to minus 3. So we want the absolute value of minus 7x plus 5 minus, what's f of minus 3? I don't know. Stick in minus 3. Minus 3 times minus 7 plus 21 plus 5 is, I get 26. So I want this to be less than epsilon. Hopefully I can get what I want in terms of what I can control, which is x plus 3. That's the value. So what we want is minus 7x. Let's see what the constant is when you add these. I think it's minus 21, isn't it? To be less than epsilon. I don't have that. I'm not saying that we got that. That's what I need to have happen. So I can factor here out of this absolute value part is minus 7 times x plus 3. Because the x plus 3 is something I get to control. Does that make sense? So we're writing down what we want in terms of something that I can deal with. Well, this is the same thing as wanting. We want, here it's x plus 3 to be less than, what is the absolute value minus 7? That's right, so this is just epsilon over 7. Look, I get to make x plus 3 be smaller than any positive number I want. What should I want it to be smaller than? It tells me. Epsilon over 7. What should I let delta be? That's the proof. When you let delta be epsilon over 7, then when x plus 3 inside absolute values is less than delta, it's less than epsilon over 7, and then you just work backwards. And you get that f of x minus f of minus 3 inside absolute values is going to be less than epsilon. Is that okay? This is good enough for the proof for me. Here's what I need to have happen. If I can get this to happen, if this happens, I'm in good shape. If this happens, I got it. If this happens, I got it. If I can make this happen, I can get what I want. Well, I can make this happen because I just let x plus 3 be less than delta. The delta I pick is this one. We got it. It's okay? Something analogous to this. Anybody else with a question? Yeah, Chuck.
I got another question. My initial issue with number 5 was that it said on some neighborhood of 1. So I was trying to do it for any delta.
Yes, no, you just fine. There has to exist a delta.
But if you were going to do it for any delta, you first prove that it's continuous on B, on the set B.
I don't think you'd have to prove necessarily by continuity. I think you could get it by just saying let delta be greater than 0, and
Okay.
you could write it down in terms of it.
Okay.
Because it works for any delta.
Mm-hmm.
And so instead of having the ones involved at the left and right when you work, you just have delta, and you just start working from there.
Okay.
And then, so your answers then might be involved in delta for the output values.
But that's not what you wanted, though.
No,
Okay.
no. It's for some neighborhood, and some neighborhood means there exists one.
Okay.
Let's check that out. You know, I said something, but we have to go back to make sure that it's following the definition. So I'm going to make sure, you know, what does it mean to be bounded on some neighborhood? So I'm looking in the book. Here's what it says. It's on page 111. And it says, let A be a subset of R, let F go from A to R, and let C be an element of R, be a cluster point of A. That's what we've written down before, remember that. we say that F is bounded on some neighborhood of C if there exists a delta. So we don't have to show it for all deltas. We just have to show that there exists one that works. Does that make sense? And as a matter of fact, remember that example that I wrote on the board, the 1 over x? So that function is bounded on some neighborhood of 1. On some neighborhood, but it's not bounded on all neighborhoods of 1. Is that okay? Mm-hmm. Good, there we go. What else? Anybody else? Yeah, okay. There's nothing else I'd like to move forward, but if there's something else, it's okay. Okay, well, I have made the videotape of the class where the recording didn't work. I redid it, but I haven't posted it yet. But there was something I said in that video that I'm not sure I actually said in your class. And so I want to put it here in front of all of us at this point again, okay, because I did it in the makeup video. But here's what we had done. You might remember we had shown that if you give me two continuous functions, algebraic combinations of them are continuous. Okay. That's the fact that we've done. Well, what I want to tell you from that as a fact, just to say this. Let me write this. From the algebraic combinations of continuous functions are continuous. Then we have the following fact. Facts. Okay, here they are. 1. If f of x is a polynomial, let's instead of calling it f of x, let me write it h of x. What's that mean? That means h of x, it looks like some number times x raised to a whole number power. Plus, that's what the term for it, plus some other number possibly times x raised to 1 less whole number power. All the way down to a sub 1 times x plus a sub 0. Okay. Then, h of x is continuous on R. Let me give everybody a second to write that down. Okay, why? Well, here's the reason. Look, a constant is a continuous function. So, this is a constant, which is a continuous function, times x. And what do I know about x? It is, I know x is a linear function. It is continuous. You can show these two are each continuous. You multiply them together, you get a continuous function. What if you have x raised to a power? Well, x itself is a continuous function. Is that okay? You multiply it by itself a bunch of times, you're just multiplying a bunch of continuous functions together. If you extend this fact about algebraic combinations to just more than 2 functions, you have a bunch of functions and you do the operations with them that are continuous, you result in a continuous function. So that means x to the n, you could do this by induction. X to the n is a continuous function. If it's continuous and you multiply it by a constant, which is a continuous function, you get a continuous function. So what I'm saying is each one of these rascals here are continuous. And then what are we doing with them? We're adding them together. And if you add continuous functions together, what do you get? Continuous function. That's why that's continuous. And then we can say something, another fact. Oh yeah, this is beautiful. If h of x is a rational function, then, oh, wait, what's it mean to be rational? Rational means h of x looks like an f of x over a g of x. Well, what do you know about f of x? It's a, anybody remember?
Polynomial.
It's a polynomial. It's a poly over a polynomial. Then, h of x is continuous for all x values except x values where g of x equals to 0. Yeah, that's it. And a polynomial is continuous. That's the top. The bottom is continuous. So as long as the bottom isn't 0, you take two continuous functions and divide them, you're going to get a continuous function. Except where the bottom is 0. Outstanding. Is that okay with everybody? Outstanding. Okay, now we're going to move to new material. So we've answered questions today. I'm glad to do that. I enjoyed it. And then maybe this was something new. I can't remember. Did I say this before?
I don't think so.
I know I said it for limits or something analogous with it. I don't think I said it for continuity. So I'm glad to have said that. And I should have said it right after the algebraic facts of continuous functions, but I failed to do so. Wait, well, we got it in now. That's good. We'll review. Well, we'll push forward now. We'll go to some new material. And so we're talking about continuous functions, what we say about them. All right. There, we talked about the square root function. Is that where we left off? That is where we left off, wasn't it? We were trying to show that the square root of f of x is going to be continuous. Isn't that right? That's where we left off. What have we shown? We've shown that the square root of x was continuous. Have we completed the proof that composition of continuous functions? We have.
Yes.
Okay. So, where we are. So, let's recall. We had this fact. It said, let F go from A to R and C be an element of A, where alpha of x is greater than or equal to 0 for all x in A, and F is continuous to C. Excuse me. Then, the square root of f as a function that's defined by the square root of whatever f of x is continuous at C. Proof. Let g of x be defined by the square root of x. Then, the square root of f acting on x is really g of f acting on x. since F is continuous at C, and G of X is continuous on 0 to infinity, and F of C is an element of 0 to infinity, then G is continuous at F of C. Thus, G of F is continuous at C. And that's by the fact that we ended with last time. But what is G of F? Well, G of F is nothing more than the square root of F. It's continuous. And that's the proof. So really, it was really heavily based on the two lemmas that I presented to you. Okay. I want to do a couple of definitions and maybe one more fact. At least keep the fact up there. So the definition has to do with continuity. Well, the definition has to do with bounding. Not bounding on some interval or some neighborhood, but just bounding. What's it mean to be bounded on the domain? So here's the definition. Here's the definition. So if we have a function f that goes from A to R, it is said to be bounded on A if there exists an m greater than 0 such that for all x element of A, the absolute value of f of x is less than or equal to m. That's what this definition is. I want to write another definition related to that. I mean, you can guess. We're going to talk about bounded. The opposite of that is unbounded. Oh, yeah. So, as a definition, a function f going from A to R is said to be. And man, this is a hard definition to remember. Unbounded on A if f is not bounded. Well, that's easy. If it's unbounded. Yeah. All right, John. Let's look at some examples. So here's some examples. if I let f of x be equal to 2x plus 1 on, we'll just look at it from minus 1 to, let's say 3. Okay? So what does this graph look like? So at minus 1, I'm down to minus 1. And at 3, 1, 2, 3, we've got 7. There's 7. This is the function I'm looking at. Yeah, there it is. Perfect. I've got a theorem. It's not really got my name to it, but if you're drawing the graph and you miss the dot, you just make the dot bigger. It's called the big dot theorem. I haven't put my name to it. That's what that's what it looks like. And if you said, I'm looking at that, is that bounded? F of x is bounded on minus 1 to 3 as the absolute value of f of x is always going to be less than or equal to what number? There's lots of numbers, infinitely many. What number could you give me? Worse. 2. 7 is right. 2 is not right.
10.
10. 7 is good. I'm going to write 7. Okay? Okay? 2 is no good because the function gets above 2. Okay? Is that all right? 7 is good. You got to watch out for that negative part, but the absolute value of the negative part, it only reaches to 1. Okay? Just have in mind. That's true. Let's look at another example. So I already talked about this, Michelle. If you look at f of x, defined to be 1 over x on, so my a is from 0 to 1. Okay. Here's what it looks like. 1. Okay. Then, f of x is not bounded on a. Because no matter what m you give me, this one, hey, if that was m, does it ever get above that? Do the output values get above that m, the y value? Sure. Oh, well, if you said I didn't pick that, I picked this one. Does the output value get above that? It sure as heck do. Is that okay? No matter what number you give me along the y-axis that's positive, the output values get above it. Does that make sense? So it's not bounded on that. Okay, so that's something, we got an example bounded, we got something unbounded. Okay, kind of reads here. Well, I'll tell you another one. What if you have f of x is equal to sine of x on r? Oh man, this is easy. Is this guy bounded? Is it bounded, Brad? What's it bounded by? What number does the absolute value of sine of x always less than or equal to? 1. Oh, sure as heck is. Yes, sir. Outstanding answer. You know what are outstanding answers? They're right answers. That's what I think. So funny. People say, well, you know, I don't know. He could have said, that's the right answer. Fantastic. Okay, let's do one more example. Right up here. We got that. That's every thought's wrong. As an example, one last example. What if you look at f of x equal to, what was that previous example we had? I forgot, the linear one. Very first one I did. Yeah, no, I'm talking just a few seconds ago. This is it was my first example about boundary.
2x plus 1.
2x plus 1. Okay? On R. So if I look at it on R, what would you say? Say it again, please, Dal.
No.
Is not bounded on R. Okay? That's what we mean by bounding. All right, let me get up the theorem. It's called the boundedness theorem. Now, what's the topic for functions that we're talking about? We're talking about limits of functions right now? What are we talking about for functions? Continuity. Okay, so here's called the boundedness theorem. What's it say? It says the following. It says, let I be an interval, A to B, be a closed, bounded interval. Oh yeah. And let F go from I to R, be continuous on I. Then F is bounded on I. All right, now look, this isn't perfect to what we've done in calculus, but it leads up to something we do in calculus. I'm talking about calculus. That's what this course is about. It's about theorems that we use in calculus. So I want you to hearken back. Oh, that's a great word. Hearken back to your time in calculus. You might remember a section where they say, hey, here's a function, here's a closed interval, find its absolute maximum. Find its greatest value and its smallest value. How do you know it has one? You know it has one by this theorem. That it's bounded. So there's something that's bigger than everything and something that's smaller than everything. Does that make sense? That's what this theorem tells us. It's got to have an absolute maximum. What kind of functions do? The functions that are continuous on a closed bounded interval. That's what we're saying. We won't have absolute maximum, even though I hadn't defined absolute maximum. But that's what we're talking about. Do you remember that, Brad, about doing that? Yeah. Yeah, Megan, that's stuff that's commonplace in a calculus course. But I'm sure you did it. So this theorem is what kind of allows us to get to that, be able to do it, to ensure that there's absolute maximum. This theorem is important for that. Well, how would the proof go? Oh my goodness, this is a fantastic proof. Proof. Okay. So here we're going to let I be equal to A to B. That's all it is. A to B. F goes from, I don't even know why I wrote down I. F goes from A to B to R. With F being continuous. On A to B. What do we want to show? We want to show that F is bounded. That there's some number out there that's bigger than or equal to the absolute value of F of X. Is that okay? That's what we want to show. We don't show it that way. We show it by contradiction. Okay? So the proof is by contradiction. So I suppose all the hypothesis part. And then we suppose the opposite of what we want to show. Suppose F is not bounded. Oh gosh. On A to B. Okay. So wait a minute. I'm going to write up this last part. We'll go through it. So lose time. We're not going to make it through the proof. We'll finish it up next time. What does it mean to not be bounded? It means no matter what number you give me, to act like the n, there's some x in the domain such that f of x is bigger, the absolute value of f of x is bigger than that number. So, all right, that's what it means. So, we will write that. So for each n, element of natural numbers, there exists an x of n, element of A to B, such that the absolute value of f of x to n is greater than n. N couldn't have been an upper bound for, or n couldn't be the bound for, because it doesn't have a bound. Okay, so there's some input value such that the absolute value of that input value is bigger than n. And that's my time, but I want to tell you this. Here's what we start concentrating on. We start concentrating on the X of N's. When we look at the X of N's, we're doing this for each N. So really we're forming a sequence. That's right. And the sequence lives in a dimension. And that's a closed interval. And if you give me a sequence in a closed interval, it's bounded. If you give me any bounded sequence, it has a convergent subsequence. And what it converges to is going to be in here. And F's going to be continuous at that. So F of X, or F of any sequence, has to converge to F of X. Okay? But that's going to be a problem. Because this sequence isn't bounded, so it can't converge. But F of that sequence has got to converge to F of X, but it can't. Because somehow, that's going to be, I said what proof is, but I got to write it up, because it went awful fast. And that's what we'll do next time. All right, well, I thank you very much for your time and patience.